This is the week when we really do begin to start ramping up the technical aspect of the course. So as a quick overview for all of you, if you have taken business calc before and you are retaking the course, or if you've taken calculus before and you're taking business calc before, this course is going to be structured a little bit differently, even than the other sections. We're going to cover all the same material. I promise we're going to have all the same examples. We're going to cover all, like nothing is different at its core, but I've organized it differently so that the way that this course is organized, we're going to go through the story of everything for the first unit. So I'm going to give you exposure into what calculus is, why we're playing, what the big storyline is. Like, I'm going to get you engaged in the first unit, and then we'll have test 1. Test 2, we're going to go through, we're going to redo everything, and we're going to make it technical. We're going to bring in more symbols. We're going to take care of all the proper math language. We're going to bring in those gotcha problems that everybody hates, where they're like, but I thought I knew the answer. And it's like, well, that's a gotcha, like, right? A small little detail. We're going to do that all in the second section so that you have the story and the concepts to fall back on. And then in the third part, that's when we bring in all those application problems, all those like really difficult kind of real worldy problems, because then you'll have both the theory and the concepts to fall back on. So that's just a little bit of exposure. If you have any questions on that, let me know. But we're at the top of the hour, so let's go, or the bottom, top of the hour. We're at the top of the hour, so let's go ahead and get started. Here's a quick little review for y'all. So let's have a review question. We're asking about the rationals today. The rationals have the following property. One of these is true. One of these is true. So you should now see a poll on your end. There are more rationals than irrationals. That's the first option. Rationals are the only number system that makes sense. That's where they got their name. That's option 2. Rationals are formed from ratios. That's where they get their name. That's option number 3. And then D, there are more rational numbers than real numbers. One of those is correct. Only one of those is correct. I'm going to give you about 3 or so minutes. All right, it is 1:03. All right, we started off strong and then we started to dip a little bit. So let's go ahead and share a little bit here. We will go through these answers. All right, let's start with the very beginning one. There are more rationals than irrationals. That is not correct. If you remember, I ended the class kind of saying, like, I am not 6'2". I am in a rational number nearby 6'2", right? So it's not about being rational as far as like having more of that. There's more rationals by far, a vastly larger number of forever when we're talking about how many irrational numbers there are compared to the rationals. Option 2, rationals are the only number that makes sense. That's where they got their name. That is not where they get their name. In fact, it's from part C. Rationals are formed from ratios. So the rational numbers are your ratio numbers. That's where they get their name. They're your ratio null numbers. They're the fraction numbers. Everything that you can form as a fraction using integers. So we're not talking about putting pi over 2. That's not what we're talking about. But 1/2, 3/4, all of those are great. Even the negative versions, they're your ratios, your ratio numbers. D, there are more rational numbers than real numbers. Remember that the symbol, the model I give you for the real numbers is your real number line. Your real number line contains all of the numbers that you've grown up very familiar with. And in that number line are the fractions, right? But there's also pi and square root of 2. Those appear there as well. So if the real number line holds the rationals in it, then the real numbers must be bigger because the fractions make up a part of that. So this is just to kind of keep that all on track. So if you had difficulty with this, remember that this is why we've got those guided notes and the recorded lectures available. You'll want to take a look at that because this has only been a few days since we went through this lecture. And keep in mind, we've got to retain all of this for about 15 or so weeks. So we've got a lot longer to go through and the material is going to get much more dense. So you should be dedicating at minimum 12 hours a week towards this class. That means that you should have plenty of time to dedicate to printing off the guided notes, filling those in, rewatching the lectures, watching the supplemental material, you name it, the support is out there. As well as you can always reach out to me, you can reach out to Nick, and we also have a supplemental instructor who is now available for this course. The information is posted up on Blackboard and you should be receiving an email from them soon. So let's go ahead and jump in a little bit to today. I'm going to try to give us some more models. We're going to try rediscovering a lot of things that we have taken for granted in this class or in math in general. And it's not, I don't think, anyone's fault here, right? It's definitely a plague of my profession. Math teachers in general, they bother me because they tell you all to memorize rules. And that's got to be the least productive thing that we could ever do in math class, is just memorize rules, because then there's really no purpose in doing math. Math is about modeling logic. If there's no logic, then we've entered a different field. We've entered a field of law, or perhaps religion, or we've entered a field of language. There are fields where memorizing and utilizing rules is critical. There's nothing wrong with that. But math is something different. Math is a model of logic. So I've got us started with a quote from Albert Einstein that genius is making the complex ideas simple. And today I'm going to try to demonstrate that for you, because I am going to go through somewhere around 10 different things that you have probably been told to memorize throughout your algebra experience. And I am going to simplify it into one picture. And that picture is going to be of a rectangle. One of my favorite shapes, if not my favorite shape. So versatile, so awesome. So let's jump into a few different things. Some motivations. Why do we call the operations of squaring and square rooting and cubing and cube rooting, why do we give these operations names that have shapes in them? That's interesting, right? Because if I was to talk about squaring and I was going to be in an algebra class, most people would talk about this. And I don't see a square. I see an X and I see a 2. But a square, if I was to ask anybody in elementary school, they would tell me a square is this. I don't see it. So where's the connection? What about cubing and cube rooting? Square rooting. What does this have to do with a square? And what does it have to do with a cube if I put a 3? What's happening here? There's a hidden story. What about this second bullet point? We call equations of this form quadratics. But as far as I know, quad means 4. And I don't see 4 things here. I see 1 thing, 2 things, 3 things. I see 3 things, but it's called a quadratic. Why is that the case? That seems weird. So we're going to talk about that. There's stories behind the symbols. So let's jump in a little bit. Why am I going to stress the idea of pictures so much through this class? Well, because most of us, if you have full use of your eyesight, most of us perceive and learn and process 85% of our experiences through our eyes. So that means if we're not using opportunities to draw and analyze pictures, we are leaving a bunch of our brain behind. We are not putting our brain to full use. So if you're not drawing, we're not using as many different opportunities to discover patterns as we could be. So we're going to try to make this as visual as possible, and then we'll make it formal. We'll make it formal afterwards once we have that intuition, those concepts. Let's talk a little bit. Remember that last time I introduced that there were 2 major fields of mathematics. There was the Western geometers that we started from Egypt, worked its way up through Greece, and then over into Western Europe. To the geometers, nothing exists if you can't draw it. So for example, the square root of 2 does not exist to geometers until they find a way to draw it. And they found a way to draw it by recognizing through the Pythagorean theorem that if you make a right triangle with sides of length 1, that through the Pythagorean theorem, the hypotenuse must be the square root of 2. So to a geometer, the square root of 2 only came into existence when they found it through a physical construction, a drawing. Versus if you were to talk to an algebraist from the Middle East or India, an algebraist was concerned with trying to solve equations. So to an algebraist, negatives were much more readily acceptable. They solved plenty of equations, versus geometers did not use negatives for most of their constructions. To an algebraist, things like imaginary numbers worked out great. They solve equations, negatives, zeros, all of these numbers became very, very available. So to an algebraist, the square root of 2 might have emerged from trying to solve the equation x squared equals 2. Now think to yourself for a moment, if you were to solve this equation and you were to remove the square, just think to yourself, what operation cancels away a square? Just think to yourself. Now, if you thought that a square root cancels a square, you need to make a big note in your notebook right now. Put a star next to it and say if that is incorrect. We need to call that out early. Square roots do not cancel squares. I know it's going to throw a lot of you off. They don't cancel squares. Here's the correction. You're going to understand when I tell you. Square roots do not cancel squares. Plus or minus square roots cancel squares. And this is critically different, because what's happening, and I'll sketch this out for you, the plus or minus square root cancels with the square. Those annihilate, and I am left with x. On the right-hand side, however, I have plus or minus, and then the value of square root of 2. So it's not square roots. Square roots do not cancel squares. Plus or minus square roots cancel squares, which is why the algebraist would recognize that there are actually two possibilities to solve this equation, a positive and a negative. Plus and minus is not something that we tack on because we have to remember through a rule. It is literally part of the operation that cancels squares. Plus or minus square roots cancel squares, not square roots. We've talked a few different models. We've got the piles and holes idea, right? So we've got piles that represent positive numbers, our natural numbers, our counting numbers, and then we talked about holes, how that can be thought of as our opposite. I'm going to be moving away from that model and more towards the blocks and anti-blocks model that I introduced to you before. And you can think of these as piles that are kind of protruding from the page, these one blocks, and the negative one blocks are holes going into the page in such a way that I could take those piles and I could fill in those holes, or I could collect these two things together and I could cancel them away. And it's from that that we get to see that negative 2 plus 3 is what leaves us with 1. 1 is a remainder. So we have the blocks and anti-blocks. And I use this because it is going to make organization possible. And organization is going to be critical for us being able to determine properties and patterns of numbers. So let's talk about one that we were told to accept as a rule. How about this one? Why does 3 times 2 equal 2 times 3? A seemingly simple question. I'll give it to you. Most of you would say, because they both equal 6. And that's a great answer. But then it loses the opportunity for a pattern. Is that because we did that calculation? What about 3 times 5 and 5 times 3? Would that also work? Do we have to check that in our head? We have to figure out they're both 15. Okay, what about the numbers in between? What about the numbers after? Do we have to go through every single number and check it in order to determine that this will always be true? Or better yet, if we just find a few examples, let's say we check 5 different combinations and they all work, we say, you know what, we're good to go. I checked 5 of them. All of the forever number of numbers all have to work that exact same way because I found 5 that work. Like, think about that. Think about the hubris that would entail. I walk out my door and I ask a couple people what their salary is, and I find 5 people who tell me that they make 6 figures a year, and I say, I know what, every person in the world makes 6 figures a year. I found 5 people who confirmed that. Must be. That's insanity. We would never do that. So let's not do that with numbers. Let's not say I've collected 5 data points, so all of the numbers have to behave that way. Instead, let's take this and break it down into a story. Let's break it down into a story, because we know that 3 times 2 can be thought of as 2 times of 3. And similarly, 2 times 3 can be thought of as 3 times of 2, or vice versa. So let's take this and let's model this, shall we? 2 times of 3, well, here's 1 time of 3. I'll model it with my blocks. That's 1 time of 3. I have made 3. And if I wanted to do 2 times of 3, I would copy paste that below. That's 2 times of 3. Excellent. 3 times of 2. 3 times of 2 would be 1 time of 2. And I could copy paste that below to make 2 times of 2, and then again for 3 times of 2. And we can ask ourselves, must this always be the same? Well, with this organization, we can see that there's a rectangle that forms. And that by switching the order of the multiplication, I have not changed the rectangle. I have simply changed my perspective of it. I have tilted my head sideways. That tilting my head sideways doesn't change the properties of the rectangle. It just changes how I am describing it. So sure enough, 2 times of 3 has to be the same as 3 times of 2 because it's the same rectangle. It has to be. And from this, we can say through an extrapolation of logic that has to be true no matter what the 2 numbers are. We'll call this the commutative property. of multiplication. The idea that a times b is equal to b times a regardless of what the numbers are. It's not because we've checked them all. It's not because we found a few good examples. It's because I can always imagine that if I was to draw a rectangle with dimensions a times b, that I would be able to flip that rectangle and describe it as b times of a. And that it wouldn't change the rectangle. It would just simply change my perspective. We're not changing the meaning, we're simply changing the appearance. And that's where we get the commutative property. The commutative property comes from the word commute, which many of you experience today as the process of trying to move towards campus through a large amount of snow. It's about moving, right? Commuting means moving. So commuting is just simply the ability to move A from the left side to the right side and vice versa. Which is why we're able to do it with addition as well. That would make sense to us. Having the piles in the sandbox, whether I look at the piles in the opposite order, does not change the number of piles. So I have that for addition. Subtraction and division, though, doesn't work for them. And you can explore why on your own if you'd like. Let's talk about division a little bit. How many of us grew up learning about division? And if we were going to have to teach a small child about division, we would reach for this one right here. Long division. Anybody here remember back to 4th grade and have very fond memories of long division, like good times in the past? We're like, oh, that was a good time. I can't wait to go do some more long division. I do long division every opportunity I got. It's just so awesome. It's so great. No, none of us like that. And like none of us enjoyed this period of math unless you're just a very procedurally oriented person, in which case, great. I hope you're going for a career in that. But in truth, this is not something that's intuitive. And it makes sense why it was such a pain for us. Let's take a moment and remove our experiences, remove our knowledge at this point as college students, and let's just look through this through the eyes of a child. We have taken something that we would read from left to right. And despite every other class telling me that I should read from left to right, an English class telling me I should read from left to right, and me writing from left to right, I'm going to take this opportunity and this opportunity in math only to write it from right to left. And then on top of that, I'm going to start to break apart this number in a way that I have not broken apart any other number before. I'm going to consider not the number itself, but just the first largest part of it. And I'm going to recognize that 4 does not go into 1 any amount of times. And I'm going to now turn this division problem into a multiplication problem. So it now becomes 0 times 4 equals 0. And then I turn the multiplication problem that came from a division problem into a subtraction problem. And then I'm going to take not the rest of the number that I forgot before, but only a small bit of it, and I'm going to move it down. And then I'm going to repeat this, and I'm going to repeat this over and over and over again. To a child, this is an infuriatingly unique process that has very little conceptual understanding as it appears in front of them. Now, that's not to say that this is a wrong process. You're welcome to do it because we know there is logic behind that. There's nothing wrong with this from its own process. But this is not its meaning. This is just a way of getting to the answer. So instead, let's talk a little bit about what actually is division. Division is the idea of grouping. It's the opposite of multiplication. So what we can do in order to keep our life nice and simple is we can just think of division as the opposite of what we did before. So if we have now agreed that 3 times of 2 and 2 times of 3 makes a rectangle, then let's consider what division might be. Well, if area is equal to length times height, then I should be able to rearrange this equation to make it area divided by length is equal to height. And then that, therefore, allows me to model this entire thing as a rectangle. I'll put the 1244 as the area because it's the number that's being divided. And then the divided by 4, the 4 would need to be one of the lengths. And in this way, we could determine that what we're looking for is the other side. But because we have a visual model, recognize some of the creativity we could play with. We could play with looking at this, not through that long procedure with many, many problem areas, but instead, what about looking at it as 1244, the same way that we would have read out loud as it was a story. Now, if I'm trying to look for how I take care of that rectangle in segments, I can do so by saying I have a segment that's 1200 big and a segment that's 44 big. Well, then that means that this would have to be of dimensions 300 by 4 in order to get the 1200, and this would have to be of dimensions 11 by 4. So what I have is 311, so this must be 311. It's faster, it's quicker, it's easier. It comes about from grouping. It comes about from the meaning of division, the story behind the symbols. It's what allows us to see things like the distributive property. Again, something that we've been told to memorize. Let's not memorize it. Let's instead understand it. We have 1244. I can break that into 1244. It's what we have. And then if I'm trying to divide that by 4, that means I'm forming rectangles. That means I have rectangles where I've determined one of the side lengths. The side length is 4. Well, that allows me to say I could consider 1200 divided by 4 and 44 divided by 4. And that from those miniature problems, that chunking out process, that's where we get the 300 and the 11. Similarly, it's what allows us to see that multiplication has a distributive property, because after we simplify that on down, we see that what we did when we did the 311 by 4 rectangle, that was really us looking at it as a 311 by 4 rectangle, and that the 300 by 4 produced part of the area and the 11 by 4 produced the other part of the area. So it allows us to say that we are able to do 300 times 4 and 11 times 4 to get us parts of our total, the 1200 and the 44. So rectangles. Rectangles explain so much, right? And it keeps it intuitive. If we wanted to, we could go through this and we could find the 300 columns and the 4 rows and count the 1200 square units of area. That would be fine. That would be totally, totally fine, because it has to be. You can't break this if you try. All right, why can't we divide by 0? This is a great one. Do me a favor, throw into the chat why we can't divide by 0. Give me all those rules, everything your teacher told you, everything the high school teacher said why we can't divide by 0. I want them. Collect them for me. Throw them all over at me. What do we got? Why can't we divide by 0? What have we heard? All right, let's see some of these ideas. What do we got? Calculator can't do it. I love that one, right? Because if technology is limited, so is humanity. No. Plenty of things we can do calculators can't do. It breaks the calculator. It's not possible to take a 0 piece of something. I like that one. That one's good. Let's break that one apart. 0 piece of something. Well, if I have 4 objects and I want to take a 0 piece away from it, wouldn't that leave me with 4? That seems doable. All right, no problem with that. You can't separate something into nothing. I like that. But I also have never had success dividing something into negatives. So that must mean negatives don't work either. Bummer. Cannot divide something by nothing because it's a rule, I guess. It has no values. It's undefined. I like undefined. Undefined just means I don't have an answer to give you. Why? Did you just not try? Can't take something out of nothing. 0 is nothing. Can't cut a pizza into 0 pieces. I like that. Can't cut a pizza into 0 pieces. All right. So if I can't find it in the real world, it doesn't exist. It makes God angry and creates black holes. Yep, I've heard that one. Right. Think about all these ideas. Like, this doesn't sound like math. Right. This doesn't sound like, maybe science at best, but really just sounds like we're all calling. We're just saying, you know what? I haven't figured out an answer, so there must not be one. That sounds like hubris. Let's compare a couple of different things. What about the you can't divide nothing arguments? Well, divide nothing would really be this, wouldn't it? Divide nothing. Okay, I can do that. That's no problem. Let's start with 0 things. Here's 0 things. I'll section it off on my paper. That's a whole bunch of nothing right there. And I can break that into 4 pieces. There's me breaking it into 1, 2, 3, 4 pieces and considering one of them. 1/4 of 0 would be that little sliver of nothing, which would represent, yes, still nothing. So that works out just fine. So 0 divided by 4 seems to be just fine. Why not 4 divided by 0? Why doesn't that work? Well, let's use the model of rectangles. I'm going to try to keep, like, I'm going to try to keep this a one momentum party right here. We're going to try to do rectangles. Let's just play around, shall we? So if we are playing with rectangles as our model, we have 0 divided by 4. That's an area divided by a length. Let's make that a rectangle. So I have a rectangle with area 0, and I have recognized one of the sides is 4. This division problem is just simply asking me, what's the other side? What's the other side? 0. Has to be, right? Because that's saying that I can't fit anything in here. The only way I can't fit anything into a rectangle is it must be flat. The only way for it to be flat is one of the sides has to be 0. That makes this 0. There you go. That's why we can divide 0. The rectangle helps to explain it. One of many models, but the rectangle is a great one. Let's now flip it. Let's do 4 divided by 0 as an area problem. That's me starting with a rectangle whose area is 4. I have identified one of the side lengths as 0, and I'm asking you for the other. What's the other? Four wouldn't work. 4 by 0 would not produce an area of 4. Ben says it can't be anything. How come? Anything would work? All real numbers? That means I could throw 4 in there? No, 4 doesn't work. 5 doesn't work. 18 doesn't work. There we go. I like that, Kyle. Excellent explanation. Anything times 0 is 0. So what is the answer that goes here? There isn't one. There's no answer that satisfies this storyline. So why is this undefined? Because there's nothing that works. There's no number that works. It's not a conspiracy. It's not my calculator against me. It's that we were set up in an illogical situation from the get-go and then prompted for a logical answer. There's none. There's nothing that's going to make that happen. There's no answer I can define that satisfies the setup. So there you go. It's undefined. Undefined. Nothing works. It bothers me how weird 0 is. It bothers me too. There's a reason why it took us thousands of years as a civilization to accept it, right? 0 is weird. I like the rectangle model. It'll save you. It'll save you every time. Is it 0 divided by doesn't work or divided by 0 doesn't work? Make a rectangle. Make it area equals length times width. Y'all been playing with it for years. Put it to your advantage. All right. Let's talk about this one here. By the way, you're going to need to keep in mind the whole divide by 0 thing. We're going to do that in calculus. We're going to come within a hair's edge of that for the rest of the semester. We're going to try dividing by 0. It's not going to work. And then sometimes we're going to find creative strategies where it seems to work. But it's not that it does work. It's because it doesn't. We just showed it won't work. Like it won't work. We can never divide by 0. It's not because I'm preventing you. It's because it doesn't make sense. But we will get creatively close. All right. What about 2 negatives? Why is it times a positive? Well, there's a story here. Let's break this apart. Remember that negatives you can think of as opposite. Opposite means negative. So this is the opposite of 2 times of negative 2. Now, I know how to draw negative 2. I've shown you all how to draw negative 2. We can make it with those little anti-blocks, right? So I can put in negative 2. We'll make that negative 1, negative 2. Now, if I want 2 times of negative 2, that's no problem. That just means I got to copy paste it below. I got negative 1 and a negative 1 again. So I've got 2 times of negative 2. Now, what is the opposite of 4 wholes? It would have to be 4 piles. So that's why through the process of making this opposite, we take this to positive 4. So negative times negative is a positive because what you have is a contradiction of opposites. You're looking at the opposite of 2 repeated. Well, that's going to force us back into the realm of positive just by understanding that an opposite of an opposite undoes itself. So there you have it. Negative times negative is a positive because we're using it as a story. So don't fall into the trap of symbols and needing to do rule. There's none of that. There's absolutely none of that in math. It's all stories. It's all decompressing the notation. It's all trying to understand because there's so much behind it. Like this, everything that I've done so far in here, right? We could go and convince a grade school child like why this all makes sense. And it's a bummer to me that I was never shown it earlier because I think it could have exposed a lot more patterns. What about this one? Why is x squared called x squared? Well, let's break down the notation. Again, let's start with x squared. We know that that means 2 repetitions of x, and that makes multiplication. We know that multiplication is something that can be related to a rectangle, like an x by x object. So I've got one drawn right here. We can label one of the sides dimensions as x, and the other one can be x as well. And that makes this have to be an x by x object or an x square. And it's in that way that we get the square numbers. Why is 100 a square number? Because I can represent it by a 10 by 10 square. So it's a rectangle, very specific kind of rectangle, a square. So squares are physical shapes. So we've now got enough drawings and insights that we're going to start taking these together and using them to make patterns. Let's look at a couple of the different shapes that originate as a result of this model. So we have our x squares. Those are x by x objects. How big is x? Not important, right? 4 by 4 will make a square. 10 by 10 will make a square. 300 by 300 will make a square. So it doesn't matter. Don't worry about counting the blocks. Understand the model of logic. It's in our mind. It's a square. Doesn't matter how big it is. It's going to be a square. What are its dimensions? I'll tell you later. But we can imagine it as a square. I can sketch it as a square. It's a square. So I've got a square here. What about x cubed? Well, that would be something with a width, length, and height that are all x. So that makes an x cubed, a literal x cubed. That's where it gets its name from. It's a cube. All right, well, what about this thing right over here? This is an object that has the same height as my x square. So it must be x tall, but it only has 1 unit in width. So this must be a 1 by x object. That makes this an x rod. You could think of it as an x rod. And then this object down here has a whole bunch of 1 by 1 by 1 dimensions. So that must be a unit. That's a 1. So now we've got shapes. We got shapes that contribute to the idea of what is 1, what is x squared, what is x cubed. They are literal objects. You can go build them at the hardware store. You just got to tell me what its x means, and I can physically construct that. And better yet, I can organize it. And it's in the organization we'll find some patterns. All right, factoring. Let's talk factoring a little bit. Why can 6 be factored, but 7 cannot be factored? It has nothing to do with the symbols, the numbers, and the calculator and what it tells us. It's about organization. 6 units I can sketch out like this, which means I can represent and organize 6 units in a rectangle. I can make that a 3 by 2. There you go. Andrea's got it in the chat. Excellent. Yeah. It's because I can organize this as 3 by 2 versus 7. If I take those 7 units, there is no way to form a rectangle except to simply have them lined up, which is a 1 by 7. So the 6 by 1 can be reorganized into 2 by 3, but the 7 cannot be organized into anything else except for something that makes that 7 apparent. So factoring is organization with rectangles. It's literally finding the dimensions of a rectangle. So we've got factoring is organizing with rectangles, multiplication is rectangles, division is rectangles, distribution is rectangles, multiplication and commutative property is rectangles. Oh my golly, shall we keep going? We got plenty of rectangles here, but why stop with the numbers? Let's talk about variables, because we've been through algebra class. We've been playing with factoring with variables. Well, what's happening here? I've got an x rod and I've got an x square. Well, I can take those and I can organize them. I can take an x block and I can put it on top of my x square and I can explore its dimensions. After all, this has to be a width of x. And this has to be a height of x. And this is a height of 1. So that means that this entire rectangle can be represented with dimensions x by x plus 1. Which is why x squared plus x can be written as x times x plus 1. Because it's factoring, it's organization. It's nothing different than the 6 is equal to 3 by 2 thing we just did, right? The moment you tell me what x is, this is going to be something I can physically construct. If it's 100 plus 10, that is guaranteed to be 10 times 10 plus 1. Has to be. Has to be. Now's where it gets really fun. Let's talk through quadratics. Now again, quadratics is a word that has quad in it. Quad means 4. I only see 3 types of shapes right now. We've got our a number of x squares. How many is a? Doesn't matter. Pick a number, play with it, and then immediately forget it because we don't need the specifics. I just have some of these tiles. What about bx blocks? I have some of these rods. And then I have some units. And I would like to try to factor them. That means organize it in a rectangle. Well, I could start by putting the big fellows in first. I could put the x squares in first. Right? So I'll just put those in. I'll stack them in, organize them. Leaves me with some space. Now, what about the x rods? I can put the x rods in. Well, it would make sense that since the squares have an x height and an x length, I should take the x objects and I should stack them against. They'll fit in quite nicely. So I can put some of them on the right-hand side of this, and I can put some of them below. So I've got the x rods nested nicely against the x squares, and that leaves me with a little space in the bottom right. That little space in the bottom right has a perfect opportunity for a bunch of little 1x1 units because they'll stack up against the small end of the rods. So we can get all those little units stacked in there together. So we can take the quadratics and we can organize them into a rectangle in this way. Oh, well, that's crazy. Have you noticed that in doing so, what we have created is something that has 4 regions? We have a region here, here, and here. In fact, we could call those quadrants and say that this is an equation that works very well with 4 quadrants. It's a quadrant equation. Oh my golly, maybe that's why it's called a quadratic. So when people look at me and they go, why are you doing all that new age fancy drawing math? I'm like, this is not new age fancy drawing math. This is like the only way we started doing the techniques in our algebra book was in the last 100 years. This has been the way we've solved them for thousands. This is about as old school as you can get. They're called quadratic equations. It's in the name. You can't argue with it. So I find it almost insane when people are like trying to argue that this is something that should be skipped in education. No, it's in the name. Why would you skip it? It's in the name. And let's recognize that it allows us to see things that we no longer have to memorize. So let's explore this organization, shall we? We have now recognized that if I have a quadratic that is of this structure, I can put it into an organizational structure using 4 quadrants because it's a quadrant equation. That puts the x squares in one region. It takes the rods, the x blocks, and it puts them in the 2 different regions, but it splits them up to do that. I only have so many to begin with. Some of them go in the top right, some of them go in the bottom left. So I'll label that. I'll put the first part of the x blocks go in the top right, and then the second remaining amount go in the bottom left. And then the units fit in nicely on the edge. Okay. Well, I can organize this as we just did into a rectangle, and I can determine its dimensions. So I'm going to use lowercase letters to show the dimensions. We already know that this is going to be some number of x lengths going across because it's those big x blocks. We're going to go across those big x lengths. And then this is where the rods were stacked vertically, where they just had a bunch of those skinny little 1 dimensions going across. So this is going to be some amount of units. We'll call that b. So I have some amount of x lengths and then b amount of little unit lengths. And on the other direction, I've got some amount of x lengths and I've got some other title for the number of unit lengths. Okay, so this is how I should be able to factor this into some form of ax plus b times cx plus d. But it's better if we now take this instead of inside out, let's take it from outside in. Let's take those dimensions over here, ax plus b and cx plus d. And let's build our rectangle from the outside in. Well, this first region has to be a times c times x times x. So this is a groups of c groups of x squares. There's a lot of x squares. All right, that makes sense. Then we have b c x, and then we have a d x, and we would have b d. All right, so that's what we would get if we construct it from the outside in. Nothing immediately amazing here, because to a geometer, we've just simply built a rectangle. But this is where the synergy happens. Let the algebraist come in, who is perfectly comfortable just playing with numbers and variables. And take a look at this. The algebraist might recognize that if you look at the diagonal, that you would get a times b times c times d times x squared. And that if you go in the diagonal this way, you would get a times b times c times d times x squared. That's weird. That means any rectangle ever if you break it into 4 regions, whatever they are, the areas multiply to the same thing if you go diagonally. Like, you want to see an example of that? Sure, let's choose some random numbers. Let's do 3 plus 2 times 5 plus 4. In other words, this is going to be a 5 by 9 dimensional rectangle. You ready for this? That makes this region have to be 15, this has to be 10, this has to be 12, and this has to be 8. Well, I know that 12 times 10 is 120, and 15 times 8 would be, oh by golly, that's 120 also. And it works for any rectangle. It's a conspiracy. It's crazy. Why is this useful? Well, one, it's just kind of pretty, right? But it's useful because it gives us insight into how we split up our X blocks. Because remember, we didn't know how we were going to split them up. We just know they do get split up. Now we know they have to get split up in a way that satisfies a truth about all rectangles. So let's do an example, shall we? Let's imagine that we are starting with this and we are trying to factor it. Ready? We're going to break this into 4 quadrants. Why? Because it's a quadratic equation. So it has to go into quadrants. Let's put the x squares in a region. Where do the 10x's go? Remember, those are rods. They're physical tiles, right? Do we put them up here? Well, no, because then I have nothing to put below it. Do I put it in both regions? No, that's too many, right? That's 20 X tiles. I only started with 10, so we're not like playing with symbols here. We're saying I have physical objects that I'm organizing in a structure. So we're going to keep it true to the meaning. So I don't know where those go yet. We'll come back to it. Let's put the 6 down here, though. I know they share no common sides with the X squares. So I better put them as far away as possible. Well, I know from the diagonal pattern that this produces 24x squared. And that all rectangles, if I can physically construct them in the real world, must share that pattern in both diagonals. So what that means is I'm looking for 2 mystery numbers to fill my 2 empty regions. They must multiply to 24, and they must consume my full 10 X blocks. So what numbers add up to 10 and multiply to 24? It would have to be 6 and 4. So I can put 6 of my X blocks here and 4 of my X blocks down here, and then I can begin factoring. This has to have a common length of 4x. This has to have a common length of 6. This has to have the remaining x that makes the 4x times x equal 4x squared, and this has to be my plus 1. So it's from all of that that I recognize that this can be factored to 4x plus 6 times x plus 1. Now here's the super interesting part. Sometimes we get different and equally true answers. Because in truth, we could have factored this a couple different ways, because we're just trying to build an area. A 4x plus 6 by x plus 1 rectangle would have produced the area we need. But also a 2x plus 3 by 2x plus 2 rectangle would have produced the area we need. So we could have chosen different factors. And in fact, if we had written this algebraically, we would have had 2x plus 2 by 2x plus 3. And we could have factored this more, right? We could have factored a 2 out of both of these. Why? Because my teacher told me to? No, not because my teacher told me to, because we wouldn't have changed the rectangle. We would have just simply recognized that I could have had 2 total rectangles whose dimensions were x plus 1 by 2x plus 3. Oh, look, those are these right there, right? There's a rectangle, and there's a rectangle, and there are 2 identical rectangles of dimensions 2x plus 3 by x plus 1. So you've got a lot of creative ways you can do factoring with quadratics. They all have to satisfy those diagonal patterns. Now, if you are an algebraist at heart, that is fine. You are welcome to do the algebraic proof of some of these things. I'm going to tell you, you're going to be sweating a little harder than the rest of us. Here you go. This is the algebraic proof. Ready? Consider ax squared plus bx plus c a quadratic. If factorable, then ax squared plus bx plus c should be able to be written as ax plus b times quantity cx plus d. Thus, ax squared plus bx plus c should be equal to lowercase acx squared plus adx plus bcx plus bd. Notice, therefore, that A is equal to lowercase ac, B is equal to the combination of AD plus BC, and C is equal to BD. Since A times C produces all of the factors A, B, C, and D, and AD, B, and C combine in order to create capital B, we can factor a quadratic if there are integers AD and BC that add to B and multiply to AC. Have at, y'all. This is what you'll find in a traditional algebra book. It's called the AC method. Why does the AC method work? Because of rectangles. Because it's quadratic functions that have to work because they're part of 4 quadrants in a rectangle. It's gorgeous. If you skip the story, you lose so much potential, right? Like there's a truth of nature that is happening. Let's do an example. It's a simple one, right? I'm going to move slow through this one. Y'all try to race me. Do it on your end, right? This is a quadratic. I should solve this with a 4-quadrant rectangle. So just race me a little bit here. I have tiles. These are physical tiles. The x squared should go in a region. I'll place those up here. Not because that's what my teacher told me to, not because it makes the numbers look pretty, because it's what we would physically do with physical tiles. I don't know where these go, and I'm not going to guess. But I'll put the 12 down in the bottom right because they would have to go there, producing a diagonal pattern of 12x squared. I know that rectangles in the real world share a diagonal property where both of the diagonals have products with their area that create 12x squared. So I'm looking for 2 numbers that consume all of my negative 13 blocks and multiply to create 12. Okay, well, that would need to be, well, probably -1 and -12, right? So I'll put one of my opposites up there, the other 12 opposites down here. I'll recognize that the dimensions I need would need to be x and x, with this one being 12, and this one being, oh, that'd have to be a -1. No, the other would have to be a -12. There we have it. This is factorable into an x minus 1 length by an x minus 12 width. Straightforward, simple. Has to be, has to be. By the way, you want to talk about why completing the square, something we all remember from algebra class? Y'all remember that thing? Yeah, would it surprise you? There's a physical square happening behind the process. I'd be happy to show you that in office hours. It's a gorgeous procedure. I think I also have some things linked in the supplemental material. What about the quadratic formula? Where does that come from? It comes from solving a quadratic rectangle. Like it's literally emerges from the rectangle. I've got a video up there. Check that out as well. But here's why I like it for this class. It will save you all points on the test. Ready? Let's take a look at an example that I see semester after semester after semester from students who do not choose to do this model. And you don't have to, right? You're welcome to solve it through some different ways if you choose. But let's take a look. Just heed me for a moment. This is a solution that I often get from students. Now I ask you, where's the mistake? Because they made a mistake. And in fact, they fixed the mistake. But the mistake is there. 2 of these lines are absolute nonsense. Well, let's do it with the area model and compare and contrast. 2x squared minus 3 makes a -6x squared pattern that needs to multiply on up to that and consume all those. So that would need to be what? -6x and positive x, which we could factor on out. Take a look at this line right here. If I was going to try to draw that as a rectangle, it'd be 2x squared plus x, and then the opposite of 6x, and then the opposite of a -3. Do y'all see the error? It's right there. They put parentheses around the things because they were told that's what you should do as a process, and they didn't recognize that in just simply slapping parentheses onto the problem, they made this read like it's the opposite of the whole last chunk, which changed the meaning. And sure, they pulled out a 3 all right, but then they got 2 things that look different, even though it should be two things that share that dimension of 2x plus 1. And they just simply corrected it in the math because it didn't work out. That's not math, that's symbol pushing. Check it. If you have the area model, you can double check it like a nice applicable Sudoku puzzle. All right, so that's all the time that I have here. If you'd like, we've got some questions. You should stick around a little bit. Next class, we're going to talk about how can you add up all of the numbers between 1 and 100 quickly in your head. 1 plus 2 plus 3 plus 4 plus no calculator. We're going to do it in seconds. And also, we've talked about square numbers and that they exist. That came up in this class. Have you ever thought that triangular numbers might exist? What about pentagonal numbers? Hexagonal numbers? Because they do exist. And there's some beautiful, wonderful properties that come about from them. We'll talk about that on Wednesday, right? Talk to you on Wednesday. Any questions? Feel free to stick around. I will be here for a bit.